Good day, everyone. Today and in the next videos, we have new topics to discuss, and these are topics under discrete mathematics. Although some of these topics can be found in the general mathematics in your high school, such as sets and functions, but some of these, like sequences, sums, and matrices, are under discrete mathematics only. So we start with sets. What do we mean by sets? As you can see, we have four pictures or images. This one is the set of balloons or collection of colored balloons. Then this is a group of students, or shall we say, specifically grade 1 students. And we have collection of fruits, fresh fruits, and we have collection of colored chairs. Now, actually, these are some of the examples of the real life application of sets. So, in mathematics, what do we mean by set or sets? A set is a well-defined and an ordered collection of objects called elements or members of the set. A set is said to contain its elements. Then we write this notation to denote that A is an element of the set A. So if you encounter this notation, this means that a specific element belongs to a set A. On the other hand, the notation A is not an element of A. So this means that A doesn't belong to the set A. So, or A is not an element of the set A. Now, there are many methods to describe sets. Sets may be described in many ways, such as roster method, set builder notation, by interval notation, by graphing on a number line, and or by Venn diagrams. Now, for graphing on a number line, we can see the explanation or the further explanation when we go to linear inequalities. Okay, we start with roster method. What is a roster method? A roster is a list of the elements in a set, separated by commas and surrounded by French curly braces. So, for example, we describe the set using roster method by listing down all the elements or enumerating all the elements. So, for example, the set V of all vowels in the English alphabet can be written as like this. V, which is equal to the set of A, E, I, O, and U. Okay? Notice that these are vowel letters in the English alphabet. So it is described as the set of all vowels in the English alphabet. And in mathematics, if we're going to translate this verbal statement, this is now the translation, the using the mathematical symbol or symbols. Number two, the set O of odd positive integers less than 10 can be expressed by O, which is equal to a set of 1, 3, 5, 7, and 9, because it is stated that O is set of odd positive integers. So you know already what are odd positive integers. It starts from 1, 3, 5, 7, 9, 11, 13. But this one, in this example, it is well defined. It is specifically given that it should be less than 10. So we only consider 1, 3, 5, 7, and 9. Number 3, the set P of positive integers is given by 1, 2, 3, and so on using the 3 dots, because the 3 dots indicate that the numbers continue in the same pattern indefinitely. Okay? So these are the examples of using roster methods in describing sets. Let's move on to the next method, set builder notation method. What is the set builder notation? This is a mathematical shorthand for precisely stating all numbers of a specific set that possess a specific property. Now, in other words, this is a mathematical shorthand or using the mathematical symbols by stating all the numbers of a specific set that possess a specific property. For example, number 1, O is described as the set of X such that X is an odd positive integer less than 10. So it is clearly described here that X which is an element of the set, is an odd positive integer less than 10. So, is x can be 5? Yes, x can be 5 because 5 is an odd positive integer less than 10. How about is x could be 10, or is 10 belongs to this set? No, because 10 is not included because it states there that x is an odd positive integer less than 10 only. It's not equal to 10. Okay? Number 2, O, which is the set of x, where x taken from the set of positive integers, where x is odd and x less than 10. So, meaning the elements of this set are those odd positive integers only less than 10. So, for example, 2. Is 2 belongs to this set? No, because 2 is an even and it's not an odd, though it is less than 10, but it should be odd. Okay? So what are the elements in this set? 1, 3, 5, 7, and 9. Okay? Now, number 3, the Q plus. This is the set of x such that x taken from the set of real numbers where x is of the form p over q for some positive integers p and q. This means that set of rational numbers positive. Rational numbers are of the form p over q for some positive integers. The plus here, um, the meaning of the plus here, meaning we only consider the positive rational numbers. And this is of the form p over q, where p is a positive integer and q is also a positive integer. For example, is 1/2 belongs to this set? Yes, 1/2 belongs to that set because 1 is a positive integer and 2 is a positive integer. How about negative 4 over 5? No, it doesn't belong to this set because it should be positive integers, the p and q. Then the third one is the interval notation with the corresponding set builder notation. This is now the interval notation from A to B. So A is an element of this set and B is also an element of this set. This means that an interval from A to B, meaning there are still values in between A and B. Okay, now if we're going to convert this one in set builder notation, this is how we write the set builder notation: x less than or equal to b but greater than or equal to a. For example, set from 1 to 3, which means in this set 1 is included, 3 is also included because of this bracket or brackets. So this means that x less than or equal to 3 but greater than or equal to 1. How about this one? An interval from A to B where B is not included because of this open parenthesis. So the bracket will only tell us that that value or element belongs to that set. But the open parenthesis will tell us that that specific value or element is not or doesn't belong to that set. So in set builder notation, this is how we write x less than b because of this open parenthesis. So x is not equal to b but greater than or equal to a. So for example, an interval from 2 to 6, this is written as x strictly less than 6 but greater than or equal to 2. Now if the question is 6 included in this set, no, because of this parenthesis. How about 3? Yes, 3 belongs to this set. How about 4? Yes, 4 belongs to this set. How about 1? No, 1 is not included here because the set starts from 2 to 6 only. How about this one? There is an open parenthesis here and a closed bracket. This means that A is not included and B is included. So since B is included, so in set builder notation, we have x less than or equal to B, but greater than A. So our example from -1 to 2, where 2 is included but -1 is not included. So in set builder notation, this is written as x less than or equal to 2 but strictly greater than -1. How about the two open parentheses, open, one open parenthesis and a closed parenthesis? This means that x belong to this set as long as x strictly less than b but strictly greater than a. For example, 1/2 and 5/4, because we assume that x is in the set of real numbers, so 1/2 could be an element in the set. So x less than 5/4 but greater than 1/2. Now take note, the notation, this one is called the closed interval from A to B, and this notation is called the open interval from A to B. Sometimes these two notations are sometimes called as half open and half closed interval. Okay, these are some of the known examples of sets. We have n, which is the notation for the set of natural numbers. Now, the set of natural numbers in Wooster method starts from 1, 2, 3, and so on. Number 2, whole number or whole set of whole numbers starts from 0, 1, 2, 3, and so on. So actually, the set of whole numbers is the set of natural numbers including 0. The third one is the set of integers. These are the elements of the set of integers, okay? 0, 1, 2, and so on, and -2, -1, to the negative infinity, the set of integers. You have to take note of that because these are um, the usual sets that we usually encounter in some books, in mathematical books or somewhere else. Then this is set of positive integers. The notation, there is a plus here. And we only consider the positive integers, start from 1 to 3 and so on. Then the Q, which is the set of rational numbers of the form P over Q, such that P is in Z and Q is in Z, such that Q not equal to 0, because if Q will be equal to 0, this will be undefined. This is what we call the set of rational numbers. Now take note, if the question is 1/2 a rational number, yes, because P is 1 and Q is 2 is in the set of integer. Now the question is an integer can be considered as a rational number? Okay, can we write an integer of the form P over Q? Yes. Z, which is the set of integers, can also is a subset of set of rational numbers. For example, 2. We can write 2 over 1, which is equal to 2, right? Now, 2 is an integer and 1 is an integer. So, an integer is also a rational number, can also be a rational number. Now, R here is the notation for set of real numbers. You're already familiar with this, and you can draw a real number line where the set of real numbers are there. Then R plus is the set of positive real numbers, so you only consider the real numbers that are positive. And the last one is the set of complex numbers that involves complex numbers of the form A plus BI, where I is the imaginary number. Okay, so these are some known examples of sets. Now we have remarked, note that the concept of a data type, especially for computer science students, because computer science students are the students who will take up discrete mathematics, note that the concept of the data type or type in computer science is built upon the concept of a set. That's why we include the concept of sets, because this can be used when you go to your programming stuff. Now, in particular, a data type or type is the name of a set together with a set of operations that can be performed and objects from that set. And for example of that is Boolean. You are already familiar with this. What is Boolean? Boolean is the name of the set. Again, this is the set of 0 and 1 together with operators on one or more elements of this set, such as and, or, and not. You are already familiar with this during our discussion when we discuss about logic. We have already this one. Okay. Now, when can we say that the two sets are equal? We have this definition. Two sets are equal if and only if they have the same elements. It's very clear that we can only say that they are equal if they have the same elements. Therefore, if A and B are sets, then A and B are equal if and only if this one is true. Meaning for every x in the set of A and in the set of B, for every x should be belong in A and also x belongs in B. So we write that A is equal to B if A and B are equal sets. For example, 2, 4, and 6, set of 2 and 4 and 6, and set of 6, 2, and 4. These are equal sets because they have the same elements. Though the order of this set doesn't matter. So note that the order in which the elements of a set are listed does not matter. Note also that it does not matter if an element of a set is listed more than once. So if the set looks like this, 2, 4, 4, 4, 6, 6, 6, 6 is the same as 2, 4, and 6 because they have the same elements. Okay? It's very clear. Another type of set is empty set. Now there is a special set. This is a special set that has no elements. This is called empty set or null set, and this is denoted by this notation or this notation. So if you encounter this notation, this is the notation for an empty set or null set. Now, for example, the set of all positive integers, okay, that are greater than their squares is the null set. Why is it empty set? The set of all positive integers. What are the positive integers again? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Now, the set of all positive integers that are greater than their squares is the null set. That are greater than their squares? For example, 1. What is the square of 1? 1 is, the square of 1 is 1, but it is not greater than 1, right? It should not be greater than 1. How about 2? 2 is a positive integer and the square of 2 is 4. But 2 is not greater than 4, right? Because it says here that all positive integers that are greater than their squares. So this statement is false, which makes the set as null or an empty set because it's very impossible to have a positive integer that is greater than their squares. Now, a set with one element is called a singleton set. Okay? Now, there is a common error, which is to confuse the empty set. Take note, this is the notation for empty set with the set of this. This one is not equal to this because this empty set itself is already a set. If you write in this way, this means that this is a singleton set. The single element of the set is this one. And take note is the empty set is a set itself. Okay, so you have not to confuse with these two. This is empty set and this is a singleton set. Okay, thank you so much and hope you learned from this video and just keep on sharing the learning that you've got from this video. Thank you and God bless.